This is chapter 14. We're going to cover carboxylic acids, esters, amines, and amides, or amides. Different ways to say it. You'll hear me say those terms differently depending on if it's at the end of a compound name or if it's by itself. Alright, and so moving forward, the first functional group that we're going to talk about is a carboxylic acid. And now your carboxylic acid is the combination of a carbonyl and a hydroxyl. That's where we get carboxyl. And so you should be familiar with the carbonyl group from the last chapter. So that's your double bonded carbon attached to some things. And then it's just so happened to be attached by a hydroxyl group on one side, so I call it a carboxyl group. You have been using a carboxylic acid and not even knowing it because you've been using this thing right here. Acetic acid, aka ethanoic acid. Acetic acid is actually the common name for ethanoic acid, and you've been using it this whole semester. It's an organic compound. So, naming carboxylic acids, you're going to drop the E, and you're going to put oic acid. That's the IUPAC name. And you are probably not going to call this ethanoic acid. You're going to see this and see how many C's we have and how many H's. Well, this is your acidic H, so it goes in front. And then you've got your H's here and how many oxygens. We've got 2, and so that should look very familiar to you. This is acetic acid, but if you're naming it as a carboxylic acid, you can name it ethanoic acid. We can also rewrite ethanoic or acetic acid like this. CH3COOH. And this actually gives you a hint as to how the structure is put together. And so you'll see it written both ways. And so the acetate ion can be C2H3O2 or it can be CH3COO, depending on how you want to look at that. So I want you to really think about how you've used acetate and acetic acid and then apply that to all other carboxylic acids. And so here's the thing also about carboxylic acid. So your carboxylic acid is the highest priority of any group. It has the most stuff on it, and so it gets the highest priority. I have put a list of priorities in your intro important stuff section of Canvas, but also in, I think, chapter 12 with the other functional groups, and so you kind of have a list of priorities. If you're having trouble naming something very complicated, as far as your quizzes or exams in my course, it shouldn't be something that you have that's too complicated, but just know that carboxylic acids get the highest priority if you have more than one group there. And so you're always going to start with your C, that's your carbonyl carbon, as number 1, and then you're going to go from there. And so here we've got carbon number 1 in our carbonyl, and then we're going to branch out. We have a methyl group hanging off, and so we'll call this 3-methyl. Our longest carbon chain is 4, so that's bute, and we're going to take butane, and we're going to drop that E and say butanoic acid. Here we have benzene, so benzoic acid, and then if this is carbon number 1, we could either go this way or we can go this way. It's better to go this way, so we have 2,3-dichlorobenzoic acid. Some common names of carboxylic acid, you've got formic acid and acetic acid, propanoic acid, and butyric acid. You may see those if you work in a lab or something that uses more common names. I'm going to ask you for the IUPAC names. Formic acid is from a red ant bite, and then vinegar, as you know, is acetic acid. So let's give a practice. So pause and tell me if you can get the name of this carboxylic acid. So the first thing you're going to do is identify your longest chain. And so our longest chain here, starting at the carbonyl 1, this has to be in the this cannot be in a side chain. It has to be in the main chain. And so 1, 2, 3, or 1, 2, 3, 4, 5. And so 5 is my longest chain. You may even want to put a ring on it. But don't count your carboxylic group as a side chain. That's not a side chain. It is the part of the main thing. The last name, the functional group, is oic acid because this is 1, 2, 3, 4, 5 carbons, we say pentanoic acid. And then we have a little side chain here. This side chain is a methyl, and it's on carbon 2. So we'll finish this out as 2-methyl pentanoic acid. So pause and give me names for these guys. You should have here 2-methyl propanoic acid, my main chain. Carbon 1, 2, 3, that is prop. Anoic acid means you got a carboxylic acid over there, and then I have a methyl group hanging off of carbon 2. And then here, you have a benzoic acid. I got a benzene ring, kind of as your idea of your main chain, your benzene ring. If this is going to be carbon number 1 on my benzene ring, this is 2, this is 3, this is the lowest number I can get going clockwise. I get 3 bromobenzoic acid. And just a note about your benzoic acids. The carbonyl carbon cannot be this carbon because it has to be involved in that double bonding to make a benzene. So your benzene is its own thing, and then the stuff hanging off the benzene is going to be where you get the oic acid part. So why don't you try drawing for chlorohexanoic acid? So pause and try drawing this. You should get this as your formula, so let's go ahead and break this down. Oic acid means I have a carboxylic acid group, okay? How many carbons in that main chain, and what kind of bonds, right? So if you had an E here, that would be an ene, right? So hexene, but this would be hexane, and so this is single bonds, so we got all single bonds. And then I have a side group. Where's the chloro? Carbon 4. And so I'm going to go 1, 2, 3, 4, 5, 6. Carbon 1, 2, 3, 4 gets a chloro. Carboxylic acids make carboxylic salts, and you have probably eaten some carboxylic salts. If you've ever eaten bread or cheese that has been preserved, you've eaten sodium propionate. Propionate? Sure. It's a common name. So it's the common name for propanoic acid, or propanoate. So carboxylic acids are very polar. Look at all this polarity we get. We have these 2 different polar groups. We have the carbonyl group. We already know carbonyls are super reactive. They're very polar. We learned about them in aldehydes and ketones. And then you have another hydroxyl group that's very polar. And so we can definitely do hydrogen bonding here. We can also do a little hydrogen bonding here because I have a lone pair on an oxygen that can hydrogen bond with water. This part can't hydrogen bond with itself, but this part can hydrogen bond with this part of a different molecule of a carboxylic acid. And so you get a very polar group. So the end of a carboxylic acid is very polar. So because of that, because of the hydrogen bonding that it forms, it will dissolve in water. 1 to 5 carbons are very soluble, and then once you get 6 carbons, you start to get less soluble, so slightly soluble, but all the way up to pentanoic acid, completely soluble in water. So you can see that as we get more polarity on this end, it kind of outpowers or overpowers the nonpolar end here. But eventually you get to the point where that nonpolar end gets too long, and then it's not going to dissolve very well. And so carboxylic acids are acids. They are weak acids because they are not strong acids, and you've memorized your strong acids. Those are all inorganic. Your weak acids, they go both ways, and you know how to deal with an acid. So just let the acid do its thing. Which hydrogen is going to come off? If you think about it, this hydrogen is attached, and I'll go back up here so we can kind of see that polarity. This hydrogen right here is attached to this oxygen, which is very negative, right? So it's going to be pulling these electrons here. If this H loses those electrons, and we get a carbonyl that looks like this H plus, this bond is pretty easily broken, and this H plus can go be donated to whatever you're reacting with, water or whatever. And so then here, you actually have really strong stability here, because if I look at this really carefully, don't I have resonance? So can I not move this double bond down here and have double bond character on both of these? You actually do that. And so this is really stable because it has resonance. And so it's not a big deal if that hydrogen ion leaves, because the leftover part, the conjugate base, is really stable. And so your carboxylic acid, this is going to come off, it's going to make hydronium, and you're going to be left with the salt, the carboxylate ion. And so we call that, it goes from ethanoic acid to ethanoate. You're going to change your ic to an ate, just like how we go the reverse in acids, like ate something icky. You feel icky because you ate something gross, I guess. I don't know how you can say that. And so you know that acetic acid is going to turn into acetate. You have seen this exact reaction before, but instead of writing our carboxylic acid like this, you wrote it like this. And we saw it do this. Alright? You have seen this before, and it's not new. It's just that now we're going to break that down and actually show the Lewis structure and the double bond here, this carbonyl group and this carboxylic acid group. So why don't you try? Let's do butanoic acid. So pause and tell me what happens to butanoic acid in water. Make sure you use an equilibrium system, so back and forth because it's weak, and see what you get. So you should get this, and so you got the butanoic. Let's just make sure you know that this is 1, 2, 3, 4, butane, butanoic acid. We're going to be losing this H, is going to go hang out with the water to make hydronium, and you're going to be left with the carboxylate ion, which is going to be called, so butane, butanoic acid. And so we're going to say butanoate ion. Alright. Carboxylic salts can also be formed from a reaction of carboxylic acids and a base. And so you can neutralize carboxylic acids like you can neutralize any acid with a base. So what's going to happen here? You're going to do a double replacement. This is your acid. Acid means H+, and so we have H+, and then methanoate, which has how many carbons? 1 carbon there. So think about splitting up your carboxylic acid into parts. You got an H+ over here, and you have all this negative stuff over here. And then you've got your sodium hydroxide or any base, and usually it's a strong base to neutralize these. And we're going to put our positives and negatives apart from each other. And so your H+ is going to go with your OH- to make water. And then you have your Na going with your methanoate, making sodium methanoate. And often we put the plus after the carboxylic acid because it's kind of a weird structure. Trying to put it all together is a little strange. But you can leave the structure just like this and then write your little Na+ at the end. That's totally fine in organic chemistry to highlight the organic compound first and then put the positive ion at the end. If you wanted to turn it back into a molecular formula, then you may want to put the sodium at the front. But here we're just going to highlight the organic part and you could write it at the front. And so to name here, you have your naming of the ion. We have benzoic acid turns into benzoate. You take the ic, turn it into ate, the opposite of the way we name inorganic acids. And so your carboxylic acid salts. Remember, salts are ionic compounds. And so now we're going to be having all of these properties of ionic compounds. So we have very strong, attractive ionic bonds. You are typically have high melting points, solids at room temperature. I want you to think sodium chloride, and usually soluble in water because they're ionic, which means they're super duper polar. And so here you've got some examples of some carboxylic acid salts. How about this one? Monosodium glutamate, MSG. That is a carboxylic acid salt. They're also used as preservatives, flavor enhancers. Sodium propionate, which is used in cheese and bread. We talk about that. Sodium benzoate. You've got monosodium glutamate, MSG. You also have sodium acetate, which is used in salt and vinegar chips to make that acetate vinegar flavor. We'll go ahead and write an equation. Let's see what happens when we put propanoic acid with sodium hydroxide and see the double replacement that we're going to get here. It's a neutralization reaction. So pause and give it a shot. So we should get this. You got your propanoic acid, prop meaning 3, so I got 1, 2, 3 carbons in my carboxylic acid. I'm going to kind of separate them out. I've got the negative, this is H+, this is OH-, this is Na+. So I'm going to put my carboxylic acid part with the sodium. So we're going to turn propanoic acid into sodium propanoate. Ic turns into 8. And then we're left with HOH, which is water. Carboxylic acids are really important in glycolysis. And so when you guys go to physiology, you will see all of this again. You can actually take a carboxylic acid and reduce it. So reducing would be think about what reducing is before I tell you. Getting more oxygen, getting less oxygen, getting more hydrogen, getting less hydrogen. In organic chemistry, reducing is losing bonds to oxygen and gaining bonds to hydrogen. And so if I have 2 hydrogens here to gain, this is what happens when you make lactic acid. And so if you've ever done any sort of low oxygen strenuous exercise, like anaerobic exercises, or if you've ever gotten a massage, you can actually reduce carboxylic acids in your muscles and produce lactic acid. And so you take less bonds to oxygen. So here in this one, you don't need to know which one it will choose, but here we can see what we're doing is we're going to be losing this bond to oxygen, and we're going to be gaining 1 hydrogen here. And then if I lose a bond with carbon, I got to gain a bond, right? So I'm going to be gaining a hydrogen here. So those are my 2 hydrogens are going here to make lactic acid. The citric acid cycle, which you will definitely learn about in physiology, is all about the oxidation of carboxylic acid. So we have citric acid here. You can see it does have carboxylic acid groups. It has 3 different carboxylic acid groups. You can think about how well does it dissolve in water. You should know citric acid does dissolve in water pretty well. Also has a hydroxyl group hanging out over here. It is oxidized, so that means more bonds to oxygen. So let's see if we can find those more bonds to oxygen. So we have bonds to oxygen here. This carbon right here gains some bonds to oxygen. And we lose some of our groups here. And the mechanism for this is not unneeded. You don't need to understand it, but you do make carbon dioxide. And so the start of the citric acid cycle is to oxidize citric acid to make alpha ketoglutaric acid and carbon dioxide. The citric acid cycle goes on till you lose more carbon dioxide to give 4-carbon succinic acid, and then you continue to oxidize all the way until you get fumaric acid. Then you have a series of reactions to all the way into oxaloacetic acid is formed. Some of these things that we've already studied definitely go in a lot of things you're going to know about in physio, and it will just help to have some background here. So I would definitely maybe keep this up for your metabolism section of physiology. Alright, so carboxylic acid kind of has a cousin, and cousin is esters. Now, have you ever taken any salicylic acid product? What about acetylsalicylic acid? You have taken that if you've ever taken aspirin. So esters are formed from carboxylic acids and alcohols. And so if I let's just look at the difference here. So here I have a carboxylic acid, so I got a carbonyl group. I'm going to keep my carbonyl group, but I'm going to make like carbonyl and an ether. And so we kind of can think of esters and ethers being similar, and then carboxylic acids and esters being similar. So you've got a carbonyl, but you've got this ether group here. So I want you to remember that an ether is like this, right? A little bat flying around. And then you have it, but it's with a carbonyl, and that's an ester. So an ester has an extra stuff. And we'll talk about how to name esters, but they're very similar to carboxylic acids. We're gonna get rid of this H right here, and we're gonna add some more carbons. So the process of doing this and making an ester is called esterification. So esterification, you take an alcohol, you take a carboxylic acid, we make some water, and we get an ester. So if you look here, we can kind of figure out what we're going to lose and what we're going to gain here. And so I've got this OH is going to hang out with this H, and I'm just going to bridge these two together. Okay, so you're going to lose the hydroxyl of your carboxylic acid, and you're going to lose a hydrogen from your alcohol. From your alcohol group, so your hydroxyl group, you're going to lose a hydrogen of your hydroxyl, and you're going to lose the whole hydroxyl part of your carboxylic acid, and you're going to make an ester and water. And so this happens under acid catalyst, that's what the H plus is there for, and heat. And look at it, it's reversible. So let's say I had an ester and I wanted to turn it back into an acetic, carboxylic acid and an alcohol. Well, I would just add water to it and it would go in reverse. So esterification, remember, is making an ester. So making an ester, let's look again. I got the OH of my carboxylic acid and the H of my alcohol. I'm going to be isolating this and then connecting these two pieces together. So it's like snipping out something and then forming a new bond there. It happens under acid catalyst and heat. This ester, propyl ethanoate, is responsible for the smell of pears. Let's try it, okay? The reaction of propanoic acid and methanol in the presence of heat and an acid catalyst. So pause and give it a shot. Alright, so did you at least get your propanoic acid and methanol written out? Let's try that. Okay, so our propanoic acid down here at the bottom, so prop has 1, 2, 3 carbons, so 1, 2, 3. And on carbon 1, because it's the most important part, is the carboxylic acid group. So we got a carbonyl, and we got a hydroxyl, carboxyl. And then we're going to have methanol, so methanol has 1 carbon with a hydroxyl group. Now, if you haven't already identified which groups are going to leave and where my bond's going to be made. So if you're looking here, you know you're going to lose the hydroxyl of your carboxylic acid. Why? Because ester has a carbonyl. So I got to keep that carbonyl, but I need to attach the carbonyl to O and something else. I need to kind of make this part turn into that ether looking part. And so I'm going to get rid of this H. So this is kind of weird because your OH, your hydroxyl of your alcohol, is actually going to separate, and we don't typically write those as separate. We don't write the bond between O and H here, but there is one. And so these two are going to come out, and they're going to make water, and then we're going to connect this carbon with this oxygen right here. So we're going to bring those two together. So looking at our product here, so just to do some highlighting to show you where we got everything, here is what is from our carboxylic acid, okay? And here is what is from our alcohol. And then here is what we have cut out, okay? So naming esters, just like how we name ethers, we're going to put the two words of everything together. And so let's look and see what we have. So looking at this ester. First, we're going to talk about the part that comes from the alcohol. So alcohol is first. Starts with an A, like alphabetical. We're going to put the thing that comes from the alcohol first. You get, if you look back here, okay, this part was from the alcohol, and this was methanol. And so this is a methyl group that comes from that alcohol. And so this is your methyl alcohol, your methanol. And then What was this part from? Well, this was from the carboxylate, the carboxylic acid, and this was, or in this case here, this was 1, 2, 3. This is a propanoate. But in this example, we have 1, 2. This is an ethanoic acid. So I take these words together, and I'm going to make methyl ethanoate. But I want to write the alcohol part first. Since A comes first. So you're going to say methyl ethanoate. And that's how we name an ester. It's like part of an alcohol and then part of a carboxylic acid, but only the 8 part of the carboxylic acid, right? Not the whole acid. Esters have common names too. Ethyl acetate. See that acetic acid? Right there. But I'm just going to have you worry about the IUPAC names here. So ethyl ethanoate. Let's look at that name. Ethyl, what did that come from? That came from ethanol. And this is going to help you with reactions too, going backwards. Like, how do you get out of an ester? How do you get rid of the ester? How do you make an alcohol from the ester? Well, if you have ethyl ethanoate, you're going to make ethanol and ethanoic acid. And so if you were to add water back to this guy, remember that's a reversible reaction, you would get ethanol and ethanoic acid. What about this one? So methyl would come from methanol, and propanoate would come from propanoic acid. Ethyl would come from ethanol, so we reacted ethanol with benzoic acid. See? So you can look at an ester and figure out, how did I make this? Or I can say, hey, let's make this ester. And you can say, oh, I know that I need this alcohol and this carboxylic acid, and I react it with an acid catalyst and heat, and I will get an ester out of it. Which is pretty cool, because now you really get to literally cooking and making things in chemistry. So let's look at salicylic acid. So Bayer produced an ester of salicylic acid and acetic acid named, ready for this? Acetyl from acetic acid, and salicylic acid here. So kind of a combination. I'm not going to have you memorize those kind of combinations, but that is acetyl salicylic acid, and that is what aspirin is. But they did the same reaction. They're just putting together these, instead of putting together an alcohol, and they put together these two acids. But you can see I am getting rid of the OH here and the H here and connecting these two. We're doing the same exact thing. I'm just getting rid of that water. It's like a dehydration, right? You could also make oil of wintergreen, methyl salicylate. So if you ever like wintergreen anything, that's how we make that. We make it with methyl alcohol and salicylic acid. So go ahead and try to name this ester. And if you can, tell me what alcohol and what carboxylic acid you would get if you, or what you would need to make it. Alright, and so can you find the place where you kind of get your split? It's right here. And so on this side, you got your carboxylic acid. On this side, you got your alcohol. And so 2 carbons with an alcohol is called ethanol, right? And then 1, 2, 3 carbons of a carboxylic acid is called prop, because I have 3 carbons, anoic acid. So I get propanoic acid and ethanol, right? But in order to name it, I name it with what first? I name A first. Alcohol, alkyl group first. So what's the alkyl group for ethanol? It is ethyl. And then I name the propanoic acid. We changed the ic to 8. So ethyl propanoate is the name of this ester. And you know what you need to make it. If I said, hey, I need you to make ethyl propanoate, you will grab some ethanol, and we grab some propanoic acid, and we would react it with heat and an acid catalyst. So here, taking you through all of this. There we go. Great. So here's the structure. It wants you to write the common name. You do not have to write the common name. Just the IUPAC name is fine. Okay. So go ahead and pause and do that. Did you find the place where it shifts or it splits? Boop, right there. Between your carbonyl and your kind of ether section. So over here we got our alcohol section. And the alcohol is 1, 2, 3, which is propanol. And we got 1, 2, and this is, you remember? Right? Ethanoic acid, also known as acetic acid. And so we're going to name who first? The alcohol comes first, so we're going to call this propyl ethanoate. So propyl, here's your propyl group. Here's your ethanoate. You can also call it propyl acetate, because you can say ethanoate and acetate are the same thing, right? Yep. Esters in fruits. And so esters are very volatile, meaning they turn volatile. Means easily evaporated. So easily turn to gas. And so we smell them. And then they dissolve in water, so we taste them. So here are the esters associated with your favorite, maybe some of your favorite fruits smells. You got pears, bananas, oranges, pineapples, apricots. These esters here are responsible. Take a close look at the names and the structures to make sure you could go back and forth from the name and the structure. It may be a good idea to just go ahead and maybe cover up part of this and see if you can name it, and then look at the name, see if you can write it, and go back and forth. But now you know how to make, if you wanted to make something that smelled like oranges, well, you would take octanol, okay, the octane alcohol, and then you would take acetate ions, and you'd put them together, or acetic acid, and you put them together, and you'd get your orange smell. That's how they make essential oils. So, we're going to figure out how to take the name now, and we're going to make it into the condensed structural formula. So you can draw a condensed structural formula. If you really want to get crazy, you could draw a line formula. Just make sure you can relate those two back together. So give me a pause and do these. Alright, so starting from the end of the name, we got noic acid, which means I got a carboxylic acid group hanging out. How many carbons in that carboxylic acid group? Bute is for 4 carbons. Do I have a side chain? Yes, I do. I got a bromine hanging off of carbon number 3. And so we draw this out. I'm going to draw my carboxylic acid group. Okay. And then total, not just attached to the carboxylic acid, but here we have a total. For benzenoic acid, it's different, the benzene, and then it got another C. Right, but for here, it's a total of 4. So 1, 2, 3, so this is 1, 2, 3, 4 carbons, and I got a bromo hanging off of carbon 3, so here you go. And then you can make your H's if you want to for your full structure. If you want to do the condensed, leave myself really enough space to do the condensed. I throw my hydrogens in here. How many hydrogens for an end? Right, this one has 1, 2, 3 bonds, so we need 1 here, we need 2 here, and then your carboxylic acid carbon is all good to go. There's no hydrogens hanging out there. Right, ethyl propanoate. So this is your ester, right? This is an ester. And so we got to figure out what the 2 parts of the ester are. So we got propanoate comes from propanoic acid. See how it goes back to your nomenclature of acids. And then ethyl goes with ethanol, right? And so you could already tell me by the name what 2 things you need to make that ester. Let's put it together. I got, and it doesn't matter which side you do it on. As long as you are connecting it in the right place. And so typically we'll put our carboxylic acid first. And so let's do our carboxylic acid, because you want this end here is going to be where we cut this off and we connect it with the alcohol. So it may actually be easier for you to write an ester by starting with these other 2 things. And so maybe let's do that. Let's make an ethanol. So I have 1, 2, OH, right? I'm not going to draw the hydrogens. You guys, we can fill those in later. And then propanoic acid would be 1, 2, 3 for prop, and we have here. And so I'm going to get rid of these things. I'm going to get rid of the H here and H here. I'm going to make some water. I'm going to connect this carbon with this O. And so I'm going to go ahead and write my carbonyl. It's going to be connected to this O, and this O is then connected to these two C's. And then I can just fill it in if I want to. I can do the structural formula, or I can say, hey, that's an N carbon. It gets 3. It's 2. This one's good to go. That's an O. And here's your condensed structural formula for this guy. Oh, there you go. Hydrolysis of esters. What do you think that means? Hydrolysis. That means we're going to take the ester, we're going to react it with water. What do you think we're going to make? Look at these reactions. What do we get here? We get, if we put these two together and we make this ester, what do we get? Don't we get water? And then we have to do this in an acid catalyst with heat, yeah? And what does this mean? This means that it's reversible, right? So you can think about making an ester as kind of like dehydrating, right? Getting rid of a water with an ethanol and a propanoic acid, or getting rid of water, right? But if I have an ester and I add water to it, I'm going to be going backwards. You already know. You already know it. Nothing new. So ethyl acetate, or ethyl ethanoate, is the solvent we use in fingernail polish, in some plastics and lacquers. Okay, we can make sure we can identify here. This is where we get our ethanol, and this is where we get our acetic acid, right? Or ethanoic acid, right? 1, 2, 1, 2. So if I'm gonna do the hydrolysis of this, I actually am just going to get acetic acid and ethanol as my product, right? It's going to be the exact opposite. Look at that. Look at that. So if I have, now this one is ethyl acetate, so ethyl ethanoic acid, and this is going to be methyl ethanoate or methyl acetate. So where am I cutting it off? I'm going to cut it off right here. So just like how I separate it to name it, that's how it's going to separate when I add water to it. And so I'm going to give this hydroxide back to the carboxylic acid. And this H is going to hook up where it was over here. And so you're just going to be doing the opposite direction, except we're going to write it as a forward reaction now because it is the hydrolysis of an ester. Again, and look, your acid catalyst and heat still there. Same thing goes over the arrow, back and forth. Now, this is the acid hydrolysis, meaning we're using an acid here, see the little H plus, to do this. We can also do this with a base. So an ester can react with a strong base with heat. But it's not, the base is not a catalyst here. It is not being written over the arrow. So here, this is acid catalyzed. So anytime you have a catalyst, or a certain condition, it goes over the arrow. So this would be a condition that you have to add heat to make this work, and then any substance you add over the arrow would be called a catalyst. It kind of just helps the reaction go faster. Now, the base is not a catalyst. The heat is a condition. The base is a reactant. So this one is a little bit different. We are going to make an alcohol, but we're not going back into a carboxylic acid. Okay, going back one more time. Acid hydrolysis is going to make a carboxylic acid and alcohol. Okay, so acid hydrolysis makes an acid. And base hydrolysis cannot make an acid, because it's in the presence of a base. And as soon as you have an acid in the presence of a base, it is going to neutralize it. And if we go back up to where we have our carboxylic acids reacting with bases, let's just look. So I can show you. Where is this? Done so much already. Carboxylic acids reacting with a base. Here you go. So carboxylic acid reacting with the base, look at what it makes. It makes the carboxylic salt. We're just going to be piecing together things in new places and not necessarily learning totally new things. Organic chemistry is all about patterns. And so we're going to be uncovering these patterns. So if let's say, okay, for the base hydrolysis, just assume the acid hydrolysis, right? Break it apart like you know how to break it apart. Make ethanoic acid and methanol. Then I want you to react that ethanoic acid with a base. And reacting a carboxylic with a base makes the carboxylic salt. And so if I were to separate this into ethanoic acid and methanol, the alcohol is in no danger in presence of a base, so I get the methanol right out here. That's good to go. But as soon as the ethanoic acid, the acetic acid here, looks with that sodium hydroxide, I'm going to be doing that kind of that double replacement reaction, right? Except because I'm reacting it with this alcohol, we're not going to see that water being made. You have this ethanoic acid is going to turn into ethanoate, and it's going to have your sodium ion here. And so you can kind of think about these as really related in kind of secondary, we call them mechanisms in organic chemistry, where you kind of do one thing at a time. And for you guys, it's a little bit tougher, I think, because you're kind of having to memorize like all at once, but you also don't have to write out what exactly is happening to all of the electrons, and you don't have to do anything with intermediates. Okay, let's try it. Write what happens when methyl acetate reacts with water, heat, and an acid catalyst, or potassium hydroxide and heat. So pause it, give it a shot. Okay, so first, let's just figure out what methyl acetate is. So methyl acetate. Methyl acetate, so you need to know that acetate is the same as ethanoate. So this is an ester because it comes from methanol, which guess what is going to be a product for both of these. And it comes from acetic acid or ethanoic acid. Okay? So if we're looking at methyl acetate, let's draw it out. We have, put your carboxylic acid first when you're doing the drawing. So we got 1, 2. This is our acetic acid. Okay, and now this is all we have for acetic acid. Now as soon as we draw this other O here, that's going to be part of our methanol, right? Because this is where we would split it, right here, okay? And now we're going to react it with water, and under the conditions of an acid catalyst, and under the conditions of heat. But the water is actually a reactant here, just like it's actually a product in the opposite direction. And so when you're splitting this, we're making acetic acid and methanol. And I know that's kind of weird to write methanol like this, but I wanted you to see that this is where I got that water from, right? So here's your methanol. Now, when you're reacting it with a base, okay, it gets a little more complicated, but remember, plus potassium hydroxide reacts with heat, and we get, first of all, both of them are going to split and give me methanol. So I can go ahead and write my methanol. And there's my methanol. And then here, if it's in the presence of a base, I cannot get acetic acid, right? But I can get acetate. And what is the ion that it's with? Well, it's with potassium. So I can write this. There you go. Potassium acetate. Or potassium ethanoate. There we go, there we go, there we go. Alright, An amine. We got amines and amides to talk about. An amine, okay? Amine, lots of plants have nitrogen-containing compounds in them. So an amines and amides are nitrogen-containing compounds. And so an amine should sound like ammonia, because it comes from ammonia. And so amines are derivatives of ammonia, NH3, and your amine is going to kind of act like an alcohol, having primary, secondary, and tertiary. But remember how alcohols, we look at the carbon that's one away from the O. But with an amine, you look at the N and see how many carbon groups it's attached to, straight up. It's not like we have to go one away for the alcohol. It's a little bit different naming them as primary, secondary, or tertiary amines. And so your amine can be attached to, think about ammonia as like the simplest amine, right? It doesn't have any carbon things attached to it. It's just hydrogens attached to it. Take the hydrogens off and just add some carbon groups. Add some long chains of carbons, add some benzenes, and you get some special stuff here. And so amines are primary, secondary, or tertiary. And so looking at this primary amine, you have one carbon attached to the nitrogen, primary. For secondary, you have 2 carbons attached to the nitrogen, secondary. And for tertiary, you got 3 carbons attached to the nitrogen, tertiary. To me, amines are easier than alcohols because it is directly attached to the N versus the alcohol is the carbon that's attached to the O is the one you look at. But it's the same idea. And so here are some images, some ball and stick models showing you there. So kind of take ammonia and we're just going to add some carbon groups to the ammonia, right? And we're going to get our amines. So naming amine, you're just going to say what the alkyl group is, and you're going to say the word amine. If there's more than one group bonded to the amine because it is a secondary or tertiary amine, then we're just going to do them in alphabetical order right in front of the word amine, and we're going to kind of bunch it all together. And so if you want to tell, hey, you've got 2 methyl groups attached to your amine, you'll say dimethylamine. So look at this guy. So here's your amine. A primary amine is only going to have 1 alkyl group attached to it, so it's going to be, this is an ethyl, 1, 2, so we say ethylamine. Now, here's your amine. It's a secondary amine, though. It has 2 carbon groups attached to it, so you got to tell me what 2 carbon groups there are. So here's an amine. What alkyl groups are attached to the amine? Well, there's methyls, but there's 2 of them, so we're going to put 2 on either side. Remember, another carbon here would mean an ethyl group, and so methyl is just 1 carbon in the kind of the side group. And then here we got a tertiary amine. We have 3 different groups attached to our amine. And so one of them is an ethyl, and one of them is a methyl, and the other is a methyl. And it doesn't have a carbon chain to be on because the center of all of this fun is the N, the amine. And so you've got an ethyl group, and that comes first because it's alphabetical. And then you have 2 methyls, so it's dimethyl. So ethyl dimethylamine. And you can tell in the name if it's primary, secondary, or tertiary based on how many alkyl groups you have written in the name. So here you have 1 alkyl group, primary amine. 2 alkyl groups, secondary amine. 1, 2, 3, tertiary amine. Kind of like a cheat. Okay, so let's name it and let's classify it. First of all, classification's easiest. You have your nitrogen attached to 2 hydrogens, which means the 3rd group attached to the nitrogen must be a carbon. So this is a primary. And let's name it. 1, 2, 3, and that's a propyl group. So this is propylamine. Here, your nitrogen is attached to 1, 2, 3 things. This is a tertiary amine. Now we have to name every group. And so let's just go ahead and isolate these like we would if we're naming long chains of alkanes. This is a methyl. This is a methyl. And this is an ethyl. And so I'm going to combine the methyls to say dimethyl. But who comes first? The ethyl comes first. We're not doing the dimethyl before. The methyl is what's giving me the alphabetical. So this is ethyl dimethyl. It's not the di that's the alphabet, it's the actual group name that's the alphabet. So sorry about that. Don't worry about the di as acting as the alphabetical. And then amine. So how many groups? 2 groups, 3 groups, tertiary amine. Aromatic amines. Aromatic meaning I can smell it. It has an aroma. And so benzene is what you should think of when I say aromatics, things that have benzene in them. So the amine of benzene is called aniline. And aniline is in its simplest form here. And then if you have any groups attached to your benzene, you call it aniline. Assume carbon 1 for that, just like we do with phenol or benzoic acid. And then you tell me how many carbons away from it, from the aniline group it is, and then we name it that way. Now, if you have something of interest attached to the nitrogen, not to the benzene, you put an N in front of it, meaning there's a methyl, where is it? On the nitrogen. Okay, and so kind of like numbering which carbon it would be if it were on the ring, if it's hanging off the nitrogen, you put an N instead of a number of carbons. And so here we put a number of carbons to show me that it's 4 carbons away for bromo. But here, the methyl group right here is not hanging off of the ring, so it's not part of the ring structure. It is hanging off the N. And so it doesn't have a carbon number, it has the nitrogen to tell me where it is. So let's try naming these amines. And so first, I think it's helpful just to label what kind of amine it is. Here we have a tertiary amine, so I know I'm going to have 3 separate groups. I got a methyl, I got an ethyl, and I got another ethyl. And again, I'm naming based on my order of the actual side chains, not the dyes. But I do have diethyl, methyl, amine. I have 3 groups I have to account for. 2, 1, there we go. Now, I have an aniline. That's my base. This is my aniline base. Okay? And I do have a side chain. This side chain is an ethyl. Where is it? It's on the N. So we're going to call this N-ethyl aniline because my ethyl group is hanging off the N. It doesn't have a carbon number to give it. So here's some line angle formulas just to kind of reinforce that. You may want to explicitly, you cannot leave this off because then this is a tertiary amine, yeah? You have to tell me that that's a hydrogen there. So you could just write hydrogen here, right? You don't have to show me the bond, or you can show me the whole bond. So kind of how like they've done it in this first example, they really didn't show the bonds. You can always show the bonds if you want to. If it's around something special. But now for your carbon chains, you definitely want to do ends and bends. So if ammonia can have some hydrogen bonding, well then some amines can do hydrogen bonding too. So primary and secondary amines can form hydrogen bonds because they have N bonded to H, yeah? So we have an NH bond for any primary and secondary amines. Primary amines have more NH bonds, so they can form more hydrogen bonds. Secondary amines only have 1 NH bond, but tertiary amines have no NH bonds, but they do still have N with a lone pair. So they can hydrogen bond with water with only 1 part, but they can't really hydrogen bond with themselves. And so that affects their solubility, affects their boiling points, all those kind of things. And then, of course, the longer carbon lines you get, the less soluble you're going to be. If you have more than 6 carbon atoms, you really only have this one little piece of hydrogen bonding down here, and the rest of this is so nonpolar that it's probably not going to dissolve in water very well. So let's think about which of the following compounds are soluble in water. They just told us that if it's more than 6, it's probably not soluble. So let's look in here. 1, 2, 3, probably soluble. And I can make 2 places for hydrogen bonding. Here, I can make at least 1 place for hydrogen bonding. 1, 2, 3, probably soluble, not more than 6. Here, I don't have any N's. That's just butane and that is an alkane, which is insoluble. So careful with questions like that. So amines, just like ammonia, will act as bases. So you need to know that ammonia is a weak base. Well, so is an amine. Amine is a weak base. And so you'll see here my methylamine taking on a hydrogen from the water to make methyl ammonium ion. And the naming of that is fantastic because you know ammonia turns into the ammonium ion. So you just take that amine and make it ammonium. So this is methyl ammonium ion, and then you get a hydroxide ion. And we just put our little plus, instead of out at the end, put our little plus right on top of the N there. You want to make sure you're putting the plus on the N, not the whole thing. I mean, technically the whole thing is positive, but you really want to show that it's really the N that's positive now because it's got an extra H plus. And so if you have an acid react with an amine, an acid-base reaction, you actually can reduce the fishy odor because the fishy odor is the amines are the fishy odor, and then lemon juice is acid-base neutralization chemistry. There you go. And so here, if you're reacting with an acid, okay, we're going to do an acid-base reaction here. Your amine, your H is going to come here, so NH2 is going to turn into NH3 plus, and then you have your chloride ion left over, so this is going to make methyl ammonium chloride. And this is going to make dimethyl ammonium chloride. You take your amine and turn it to ammonium. And then you have ammonium salts. So ammonium salts are these things that used to be amines or used to be ammonia, right? And then you have ammonium things like ammonium chloride. And then they have these properties of ionic compounds, just like the carboxylic acid salts do. So they're solid at room temperature, soluble in water, which makes them good for medicines because they'll be soluble in your body. And so a lot of medications are ammonium salts. Ephedrine. Okay, here's some ephedrine right here. And you've seen ephedrine HCl. That means that the amine, right, was reacted with hydrochloric acid, so you get ephedrine hydrochloride. And then you've got diphenylhydramine, which is in Benadryl. Look at that phenyl. Ooh, look at those phenyl groups. How many of them? 2 phenyl groups. Okay, and maybe we haven't learned what a hydramine is, right? But you do know, you can kind of piece together some of these. And ephedrine is obviously like a term for this whole thing. And then here's an interesting piece, cocaine. And so if you have this beautiful structure here, this is cocaine hydrochloride, and you react it with a base, then you get the cocaine free base version, also known as crack cocaine. And so you get the ammonium salt here, and you turn it back into the free amine form, or free base. Literally base meaning it's basic, so it's an amine, and free meaning it's free of its ionic form, I guess. And so you can see here I'm going to take this Na and this Cl, bond it together to make NaCl, and so that means I'm losing this. This is not going to be positive anymore. See, this is my positive ammonium right here. I'm making this regular amine looking thing here, and then this thing with the basket looking form then will kind of react differently in my body. So amines in plants, any plants that contain nitrogen are called alkaloids. Nicotine is an example of an alkaloid. Look at those amines. Don't worry about the amines with the ends inside the benzene ring. Don't worry about that. But this one right here, over on the right, definitely. Look at that guy. Caffeine. Look at all those ends. Those are alkaloids. So anytime you have an alkaloid, you have a nitrogen containing compound in a plant. There's caffeine. Morphine and codeine are all alkaloids. Amines in plants. An alkaloid, you also may know, means basic, right? So like amines are bases. Alkaloid, amines. There you go. So go ahead and give me a quick pause just to make sure you got this. So you can give me a line angle formula if it's cyclic, or a condensed structural formula if it's not cyclic. So hopefully you got this. We got methylpropylamine. So you're just looking at your amine. We got a methyl group on one side. We got a propyl group on the other side. Put them in alphabetical order. Methylpropyl. We got an aniline here. Now you can go this way, or you can go this way with your numbering. Now this one is easier. This is 1. This is 2. This is 2-chloroaniline. So last part, we got amides. Amides are like amines. But a little bit more complicated. So kind of like thinking about a base, and then we're adding a little bit more. We got a carbonyl chemistry here. And so acetaminophen is an amide. So amides are like amines, carboxylic acids. So instead of having a hydroxyl group for your carboxylic acid, you got an amine. And so we get our carbonyl chemistry, we kick out that hydroxyl group, we're going to add an amine, and we make an amide. And so ethanoic acid will become ethanamide, or acetamide. How do we make amines? We call it amidation. And so amidation. We got propanoic acid. So we're going to be, just like when we made esters, you guys, we're going to be taking an H from an amine and an OH from the carboxylic acid, and we're going to be bonding these two together. And so for this one, you just need some heat. Okay, you don't need an acid catalyst, and it goes one way. You just need some heat. So you've got an amide bond, and we've got propanamide. So looking at the name of this, it is an NH2 over here, and then you got 1, 2, 3 from propanoic acid, propanamide. And now if we're making one that's a little more complicated, we got propanoic acid. We're going to get rid of this water here. Get out of here, water. I'm going to bond these two together. But this is methylamine, not just ammonia. And so we get the propanamide, right? But then look at my N. Don't I have a methyl group hanging off the N? So I got an extra methyl group. Where is it? It's on the N. So just like when we did the anilines, N-methylpropanamide is how we name amides with alkyl groups on that N. So try it. Pause and try it. All right, let's look at it. What are we going to put together? So I know I'm going to take the OH, right? I'm going to take one of these H's right here. So one of these H's and the OH, they're going to go together to make water. So I know I'm going to make water. So go ahead and write that as a product. And then I get this NH here. So if you want to kind of spread out your H's, this H goes here to make water. So I got an NH here. But I'm going to be connecting here, this N and this C. And so let's just go ahead and draw my benzene. Okay, and I got my C right here. Got my O. I got this is attached to this, right? Which is in turn attached to an H and a CH3. Yeah? Let's see. There we go. So naming amides or amides. They're named by dropping the oic acid and adding amide or amide. And so here, let's look at this. We got butanoic acid and N,N-dimethylamine. We keep the whole amine name except for the word amine. So N,N-dimethyl, N,N-dimethyl, and then we add butanoic acid, drop the oic, so that's going to go here. And we're going to add the word amide. So you got two methyls. Where are they? Both hanging off the N. Right here, your two methyls hanging off that N. So N,N-dimethyl butanamide. Beautiful. Super complicated, complex things. But remember, they're just pieces to a puzzle. So know your pieces and you'll be good. Pause, give it a try. All right, we got, we're going to cut it off right here. We're going to name it just like we named esters. And so this side I got 1, 2, 3, 4, and that is 4 for butanoic acid. And then I have this side over here, which is methylamine. Right? And then, so our butanoic acid becomes butanamide. And our methyl needs to now be explicitly stated that it is hanging off the N. So this is N-methylbutanamide. Try these. Pause them. Alright, how'd you do? You got ethanamide, or acetamide if it's a common name, and then you got N-ethylpropanamide. Here is an amide in health, urea. There you go. You got some barbiturates here, so we got phenobarbital and pentobarbital. Ooh, look at that phenyl group for phenobarbital. Beautiful. Both of these are aspirin substitutes. I mean, they help you with the fever and pain, but they don't really do anti-inflammatory stuff. It's acetaminophen. So, amides can do hydrolysis to make a carboxylate and ammonium salts. If you're in a base, you will actually make a base, and so you'll make the amine. And so let's just kind of look at the wording here. So acid hydrolysis will break it into an acid and an ammonium, okay? But base hydrolysis will make the salt of a carboxylic acid and then the full-on base amine or ammonia. And so looking at your options here, we're just going to be doing the same thing we did with esters, with hydrolysis of esters. You have to, though, react it. If you're in acid hydrolysis, we got to react it with an acid, okay? And you're also going to react it with water. And then you have your base hydrolysis, you're reacting with a base. You don't need any water for this one. But both of them occur in heat, and you get different pieces. And so if you're an acid hydrolysis, we get a carboxylic acid, and then we get a salt. So the other one is a salt, so the ammonium salt. And then if you're a base, you get the base, and I want you to know that an amine is the base, and then the other one you get is the salt. So the other thing, the carboxylic acid or the amine, one of them has got to be a salt, and the other is going to get to be the acid or the base. So acid hydrolysis makes an acid, base hydrolysis makes a base, and then the other thing is whatever the salt version is. So let's try. Pause and try to do the hydrolysis of N-methylpentanamide, either way, with sodium hydroxide. So this is the base hydrolysis. Right? So pause, work on it, come back. Alright, so you're going to be actually splitting it like this. And so I like even just writing your base up top can be really helpful. You are going to make your, now with our base hydrolysis, we cannot make carboxylic acid because it is a base hydrolysis. And so I get to make the carboxylic acid salt, meaning sodium and then this carboxylic acid salt. So we can see here, this NaO is right here, yeah? And then the other side is gaining NH. So you can tell what you're going to make. You're going to make, okay, methyl on the end, so that's methylamine. And then pentanamide is not pentanoic acid, and I just automatically go there, not pentanoic acid, because it's in a base hydrolysis, pentanoate, and then whatever your strong base is what goes in front, so this is going to be your sodium pentanoate. So draw condensed structural formulas for the following. Make sure you can draw those the amides. Okay, here they are. And then here's your concept map for this chapter.